Well, thank you to the organisers for giving me the chance to speak here. It's great to talk to everyone. I'm really sorry I couldn't be there in person, but yeah, it would have been great to be there. I'm well aware that this is the last talk of the entire conference, so I'm going to try and keep this short by speedily zipping through some updates on one of my favourite topics that Taisa was kind enough to ask me to talk about, which is to tell you a bit about some things that we've been doing recently in the Nearby Evolved Star survey. So, first of all, I'm going to call back to Ian's talk, and I know things that other people have undoubtedly talked about. Why do we need samples? Why do we need surveys? Well, the questions that we're particularly interested in is, how does the typical evolved star behave? And how much does it vary between different stars? Because we need to see what's the sort of the diversity of models that we need in order to explain the impact of evolved stars on the wider population of galaxies and how individual stars evolve, how galaxies evolve as a whole. What are some of the open problems that NES is trying to solve? Well, we know that mass loss dominates evolution, but when it happens on the AGB actually really, really matters. And how mass loss interacts with the rest of stellar physics, of course, critical to understanding how all of those wonderful things go on. But the sort of key motivation for NES is actually how much material is being returned and where does it go, how much of that is dust, and so on. So it's really a survey to understand the total gas and dust return to the interstellar medium. Another part of the motivation is really sort of what's missing from previous studies. So a lot of great work has been done to understand dust production in huge numbers of galaxies, and Martha's been telling you about some of the most recent progress. But our own galaxy has been conspicuously missing from a lot of these for a long time, because it's so hard to study the population when you're looking through the disk. But of course, the counterpoint to that is that we get all of these wonderful details thanks to observatories like ALMA, like the VLT, all of the little details and the whole history of the stars, not just the little snapshots. So with NES, we're kind of trying to do the opposite and get the big picture of as many stars as we can nearby. So we're looking at about 800 stars within 300 kiloparsecs that are selected based on their dust, estimated dust production, looking at them in CO and the submillimeter continuum. So we're looking at a large sample and we're trying to look at the large scales of every star, or of many of the stars. And what you'll see what that means in a little bit. Now, of course, a key thing to select the stars when we care about being volume limited is to get the distances right. That, of course, is an ongoing problem, evolving with time, and I'll come back to that a little bit later. But our, excuse me, our initial distance was basically based on just estimating luminosities and converting it to a distance assuming a fixed luminosity. And it turns out that actually, with comparing to Gaia, it's not as bad as we thought, and also maybe Gaia is not as bad as we thought. Probably reasonably unbiased, but not particularly precise in both cases. And I think Ian told you a lot about the work he's been doing yesterday, so I will skip over this other than to say that, I'll just skip over this and keep moving. So galactic AGB stars, obviously they're bright, so they've been studied for a long time. You may be wondering what's the difference between NES and a lot of the other observations that have been done before. Well, generally speaking, previous samples have concentrated on IR bright objects, which tends to be the moderately bright and moderately dusty and very dusty nearby objects. And so NES is really adding a lot of new objects to the lower dust production rate area by trying to be complete on those objects. And it seems like some of the most distant, dustiest sources have been undersampled before. And the other thing we're getting is kind of a more systematic look at the largest spatial scales of these objects. So what is NESS observing? Well, it's a large program on the JCMT with about 1,400 hours of observations, and then we're trying to complement that with critical observations at other facilities to make sure we cover both hemispheres and to try and get higher resolution with ALMA and the SMA where we can. Obviously, there's also huge amounts of archival data because many of these objects have been observed hundreds of times or thousands of times before just in and of themselves. So as I mentioned, these are dust selected based on dust production rate, so we could immediately sort of estimate galactic dust production within the area of within the volume of the survey. Unsurprisingly, this is dominated by the sources with the highest DPRs. They account for, I don't remember the exact number, but 90-something%, I think, of the total dust production. And the amounts we get are consistent with previous estimates, but we need to revisit this as our data improves through things like the work Ian's been doing, and as we get new models to analyze the data with. So first, I'm going to now tell you a bit about some of the gas data that the results we're getting from the gas data. Obviously, with such a huge sample and so many bright sources, the gas data are extremely rich. But the easy thing to do is to go and estimate an empirical mass loss rate from the individual lines, and we get fairly typical expected ranges. One thing we do find curious is that the sort of previously less well observed sources seem to be more likely to have more complex line shapes, so not a simple soft parabola, but double wind or other more complex shapes. We're not quite sure why yet. But the overall distribution of mass loss rates agrees pretty well with the observations in the literature. Obviously, once we've got mass loss rate and the dust production rates that the sources were selected on, we can go ahead and estimate a gas to dust ratio. It's pretty consistent with what you would expect. The observational gas to dust ratios are a little higher than the canonical estimates, but as you can see, these distributions are pretty broad, so shouldn't read too much into the sort of value itself. But the comparison between, say, the oxygen-rich and carbon-rich sample should be more meaningful, and we find that the median for carbon stars is about 2.5 times higher, which is roughly consistent with what we'd expect. And of course, we can look at this in more detail rather than just looking at simple plots, but see if there's any evidence for a trend, possibly consistent with non-constant dust to gas ratio. So if you just look at the linear regression, then you would say that, okay, dust production kicks in at about 4 × 10⁻⁷ solar masses per year. But these are dust selected sources, so we actually have evidence for dust in the entire sample, but we actually have many upper limits on the mass loss rate rather than the dust production rate. So this may need to be fine-tuned a little bit to account for that properly as our processing improves. as I was saying, we're trying to look at the big picture for many of the stars. So we're looking at extended emission on, scales of fractions of an arc minute or several arc minutes. And we do commonly see extended CO 3 to 2 emission on scales of tens of arc seconds. And in some cases, it exceeds 30 arc seconds or more in the famous cases. We know that they are enormous. So this is just some of the JCMT 3 to 2 data, but we also see clearly resolved emission on larger scales in the 1 to 0 line, as expected. The lower excitation line is bigger. And we also, in some cases, resolve the 13 CO, which we'll come back to later. And again, in the interest of keeping this talk short, I'll just skip over the ALMA results for now and head on to the continuum. So excuse me a second. So we see this great extended line emission, but we also see it in continuum. So Scuba 2 is a sub-millimeter bolometer camera for those who aren't familiar with it. So we get images of the continuum emission. And some of the sort of motivating work for NES was a pilot study by Tvisha Dalwardena, and in that we saw lots of extended continuum emission in the Scuba 2 data. It was a small sample, but there was about 3 times more flux at 850 micron than the dust models could explain. And so once we started getting NES data in, Scuba 2 data, we thought we'd better start digging into this a bit further. And so when we look at the sort of whole population, we see that the grams dust models, they tend to underestimate the sub-millimeter flux by a factor of sort of 3 to 10 at both 450 and 850 micron. Now, it's not entirely surprising, as grams is tuned for the mid-infrared, not for the sub-millimeter, but it's still quite a substantial underestimate. And so there's some sort of possibly a link between the amount of extended emission and excess. So the stars with confirmed extended sub-millimeter emission all have rather large sub-millimeter excess. We also see that the higher the dust production rate, the more the excess tends to be. So possibly that's telling us that these things with higher dust production rates have had more time to sort of fill their envelope, fill the beam, and therefore we're detecting more coal dust, and therefore that there's more excess emission as a result. However, the observed spectral indices are extremely low. They're consistent with blackbody emission rather than with what we'd expect for interstellar dust. Now, it could just be that there's a lot of very cold dust, and so the difference in the beams is sort of biasing us towards a lower spectral index. But the fact that we kind of don't see any stars at all that are consistent with interstellar dust means perhaps actually the dust is much closer to a black body than we expect, and we actually need some new dust models to explain that. We are trying to improve the Scuba 2 data reduction to try and firm up these, get better detections and more detections, turn some of these upper limits into solid detections to see if we can get on this a bit further. But that's hard, and I'll come back to that in a little bit. But in the meantime, we thought, well, what if we could just consider the average behavior? And of course, a good way to do that is to stack objects, because we've got some 800 objects in the whole sample, and we should be able to get a sort of factor of 30 improvement in the average by just stacking all of them. So Chris Clark at Space Telescope has been taking a look at this, and it was a big technical challenge to try and do this because, of course, observing stars in the galaxy, so your background is not random. It's the galactic plane, or the galactic dust emission. So we had to do some interesting tricks, like rotating everything so the galactic plane is always up, regardless of which side of the galaxy it was. Then you get this huge gradient across the images, the average image, so you actually take only half the image because one half of the image has systematically lower background than the other, things like that, and end up with a sort of combined stack that's only half of a circle rather than a full circle. And what we find is actually that there's pretty good evidence for parsec scale dust emission. So we see extended emission in the shorter Planck wavelengths where the beam is reasonably small. We see emission on tens of parsec scales in some cases. So if we take, I think this is the overall stack, we see this huge envelope, and if you sort of subdivide the stack into the highest dust production rate objects, you sort of see this as well. But if you then select only the lower dust production rate objects, this goes away, and it's consistent with just a point source in the stacks. What is quite interesting and reassuring that we're doing something right is that the dust in the point source component of these stacks, if you sort of extract that from the SED, is systematically different from interstellar dust. And as you sort of proceed outwards through through radius, it converges to ISM-like dust. So we're seeing maybe the mixing of AGV star and ISM dust, or processing as the outflow expands on parsec scales in the sort of very outermost reaches of the envelope. So really tracing the entire mass loss history on average. Okay, so I may have skipped over this earlier, but we are getting both 12CO and 13CO emission for a lot of our sources. This is a sort of change of pace again. So obviously with two lines, two isotopes each, we can try and place constraints on things like the isotope ratio. Now, of course, 12CO is mostly optically thick, so any intensity ratio needs to be treated with care. It's an intensity ratio. It's not necessarily an isotope ratio, but a small subset of sources are optically thin. And at first, we thought they tend to have higher ratios, higher intensity ratios, at least for CO2 to 1. But once we started to dig a little deeper, maybe that's not quite true. You can see the sort of the scatter of that with mass loss rate. It's obviously a little harder to tell the distribution of things in these plots, but it doesn't seem like there's actually any systematic difference between the optically thin and optically thick sources in this plot. And there's also really no real evidence for a trend with optical depth, but that, I guess, could just be a trend with mass loss rate. And that could be the optical depth confounding this. We'll have to do a lot more exploring before we can really tell for sure what's going on there. Now, I mentioned before that with the Nobuyama Radio Observatory Telescope, we actually are resolving 13CO and 12COs in many of the sources. And intriguingly, we actually see significant radial variation on very large scales, at least in some sources. So we've got kind of 3 where this is statistically significant variation, and 1 where there's not really too much evidence for change. But of course, this is, again, just an intensity ratio. We haven't accounted for the optical depth in this yet. So please don't ask me to try and explain this scientifically. This is very much an empirical result right now. Okay, and another quick change of pace. Obviously, we've got a huge number of AGB stars, and obviously they're variable. It's the nearby ones which, for the most part, are quite easy to monitor. So it would be very silly of us not to go and try and explore the interplay between the optical and near-infrared variability of our sample and all the other properties of things that we're trying to extract. Because physics here, and pulsation is such a critical feature of HEV stars. So initially we thought of trying to do this with the Lomskargel periodogram. It's very fast, but it's very difficult to sort of quantify the uncertainty that you get on your periods with that, especially when you have a sort of multi-periodic system, which HEV stars tend to be. So instead, we're adopting a forward approach where we apply a sort of multi-wavelength, multi-component Gaussian process. This lets us potentially use as many wavelengths as we want, so we can have sparser data on each individual band and aggregate data across wavelengths to try and infer the periods. This is, of course, much slower than using Lomskargel periodogram, but it's very powerful, and it's very easy to port this to GPUs and make up a lot of that time. Just one example of why multi-period, multi-component fits matter, because of the sort of multiple periods that you've got going on in these sources. If you just try and fit one period, you can get very strange results, which don't really seem to match what we see in the light curve directly. And just by, fitting it with 2 periods, you get something which makes a lot more sense. This is clearly a like 500-ish day period by eye, with some extra wiggles on top of that, which probably corresponds to an overtone. And then you get something which makes a lot more sense. When we do this over the whole sample, initially what we're seeing is trends that are fairly similar to what Ian has seen before when you compare with the dust, like how red the stars are is a proxy for how dusty they are. We need to do this in a little more detail with the actual dust production rates that we have and so on to see if this redness actually converts properly into dust production and if the trend persists there. But when we try and compare with the CR rates, there's really no evidence for any sort of trend, and they don't really seem to follow the models that Martin Groeneweghen's paper in 2009 compared to when looking at something similar. Okay, so that's kind of a brief whirlwind tour of some of the things we've done recently. I'm just going to spend a couple of minutes on some of our ongoing challenges if I still have the time. So obviously for any volume limited survey, one of the biggest problems you have is estimating distances. And right now for HEV stars, we kind of have one good but very expensive method, which is maser parallax distances, and a lot of other distance estimates, which can be good in certain regimes and then have their issues in other regimes. And so this is a sort of quick comparison of 3 of them. Luminosity distances, where we just assume a fixed luminosity for everything. Period luminosity distances, where you use the period and the period luminosity relationship to get a distance. Or I think this is the geometric distance estimate from Corinne Baylor-Jones, which is basically bootstrapping the parallaxes with a model, a simple prior for the distance. And you can see that there's a lot of scatter between all three approaches, and in different ways depending on the different combination. But they all sort of point to the same approximate median. So they're probably all in the big scale roughly unbiased, but have a lot of scatter. So the period luminosity distance and the luminosity distances are statistical estimates. They're great for sort of getting the overall population roughly right, but in individual cases, they can go very, very wrong. Whereas the Baylor-Jones distance is more unbiased but imprecise for everything, so should give you a reasonable estimate of the sort of maximum a posteriori distance. But we are not too sure about the uncertainty on this for AGB stars yet, I would say. So to do this better, we really need some sort of Bayesian distance estimates tailored to AGB stars. And I know there's great work going on already. As I mentioned, period luminosity relationship is great for populations, but you need quite a lot of care if you want to apply it to individual sources. And I know people out there like Jason Sanders are doing great work to improve this. But ideally, we need to try and combine all of this information with extinction maps, with models, with everything we think we know about AGB stars already across the whole population to do this better, which of course is a huge problem. But hopefully we'll be able to do that soon. Another big problem NESS has is that really to measure things like mass loss rates, dust production rates, we need to do this with radiative transfer models because there's so many confounders affecting that, optical depth, temperature effects, etc. But the parameter space is very degenerate. And so we really need to understand those distributions, and we really, really need to do this with Bayesian inference. But full radiative transfer is really, really slow. So the obvious solution is maybe machine learning can save us. Well, maybe. I'm not sure if you've seen this position paper recently. The typical approach of generating a lot of radiative transfer models and then trying to emulate them is actually quite problematic because of confirmation bias, which goes into the models, into the machine learning part. So are there other ways? Well, yes, actually. Emulation is not the only approach you can take. There is a great ongoing evolution in neural estimation type of likelihood-free inference. The idea is basically you generate a whole load of noisy synthetic observations and you train a neural network which can learn an invertible transformation between parameters and data on that sample of synthetic observations. And then you go ahead and you feed it the data, and it will just immediately spit out the distribution of the parameters. So you immediately get posterior from that network. So we've been testing this on some simple cases, for example, to learn the amorphous carbon to silicon carbide ratio in LMC carbon star. So to do this, we have to model everything, as many other properties of the AGB star as we can, but I'm just focusing in on the abundances on the right for now. With neural inference, this took 3 days. For comparison, when we tried to do this with MCMC, we gave up after 3 weeks and looked at the results and found that yes, it had just finished burning and would need a little more time to finish properly. But the great thing about neural inference is that it is amortized. So we've spent this time training for one source, but we could just now throw hundreds of other sources at the model and get free posteriors out of it. So 3 days for training and then fractions of a second for each individual source to get its posterior. Another issue, which I'm sure I've complained about at similar conferences before, Scuba 2 is a brilliant instrument, but because you're recording time series, you have to reconstruct an image from the dataset. And we're really looking at sort of one of the limiting cases of this data reduction. We have a bright compact source, and we have a faint extended halo around it. And generally speaking, the image reconstruction approach taken in the Scuba 2 pipeline is really good at doing one or the other. So when you change the hyperparameters of your data reduction run, you can completely change the image you get. So on the right here, this is just 6 different reductions of the same data set, 2 different algorithms, and then a bunch of different hyperparameters. And as you can see, it's changing completely, completely different outputs. So we're still trying to optimize this to get the best images we can, tuning hyperparameters. But for the future, maybe we need to think about adopting some of the things that the interferometry community has taken on board, like regularized maximum likelihood imaging to reconstruct bolometer images. Okay, so that is the end. Hopefully I've finished fairly early so that everybody can enjoy the rest of the afternoon. Thank you again to the organizers for inviting me, and I'll stop here and take any questions.
Well, I have one to begin. So you've talked about dust production rate quite a lot, especially earlier in the talk. Can you tell me what the uncertainties on your dust production rate are?
I can give you an estimate. It is something like a factor of 3 or maybe an order of magnitude. I'd have to check with Sundar for the exact numbers because he's the expert. But yes, they are significant and comparable to the uncertainties on the empirical mass loss rates, I think.
Okay, and actually how roughly are the dust production rates calculated?
Right. So we use the grams model grid, which is a grid of radiative transfer models sort of calibrated on the LMC. And then, yeah, we use the photometry from the infrared all sky surveys, 2MASS, IRS, etc., and fit the photometry with the grams models, which gives us sort of a distribution of the best fit and the 100 next best models. And we use that to give the dust production rate and an estimate of the uncertainty.
Hi, Peter. I was curious upon the way how you are now deriving the mass loss rates. And maybe also will make use of making an advertisement. I think that the POM methodology that has been developed by Frederik de Keuster might be very useful for your purposes. So that's it's a kind of a inverse radiative transfer, goes extremely fast. And it takes into account all kind of loss functions, so regularized, as we say. And so then out of that comes then density and velocity. So that might be very useful for the NEST team to have a look at.
Yes, thank you. Yeah, so far we've just been doing it empirically with Sophia Ramstedt's sort of empirical formulae. But we would very much like to do things like using Frederik's work. I talked to him last year when he was sort of playing around with what I think sounds like it turned into.
Yes, it's an archive. It's an archive, yeah. And we got a few comments in. They were easygoing, but we still have to implement them.
Cool. So yeah, I would love to talk to you and Frederik more about that. Because it sounds like it could be really useful to us, as you said. Yeah. Thank you.
Yeah, drop us a line and we can organize a meeting.
Cool.
So what does this paper about machine learning actually say, more or less?
You mean this one?
Yeah.
Basically, it says there are things that machine learning is good at in the natural sciences and things it isn't. So one of the things it is not particularly good at is emulating a grid of models. Because you encode certain biases from the construction of the grid and the choice of the neural network to emulate the grid with. And that can be a problem, so you should be very careful when you do something like that. But there are lots of other things that machine learning is good at. Classification is obviously something it's very good at, image segmentation, etc. And we shouldn't stop using machine learning for those things. We should just critically evaluate the things we do use machine learning for in each case and see if there's any reason why it may not be up to scratch.
Okay, so there's no sort of yes or no answer to that question.
Yeah, so the position, is machine learning good or bad for the natural sciences? Yes, it is good and bad for the natural sciences.
I just have a quick one to finish off then. You were showing the 12 to 13, I think, CO ratios with distance from stars, and the Myra one looked a bit wild.
Yes.
Is that real, or is that maybe background contamination?
So I think this part here is real, and then I expect the noise just blows up because this is the 12 to 13 CO intensity ratio, right? So when the 13 CO goes to 0 and gets noisy, the ratio just explodes. So this part of the plot is just an artifact. This part is probably reliable with sort of no real evidence for any variation.
Okay, that's actually comforting. Thanks.